तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture we saw about groups. We also what is a subgroup and under what conditions a subset of a set under a particular binary operation can be called a subgroup. We saw that it is enough if we check for the closure property. So, once the closure property is satisfied, the other axioms will be automatically satisfied. That is what we saw in the last lecture. We also saw what is meant by an abelian group. A group has to satisfy four properties: the closure properties, the associative property, existence of an identity, and for each element we should have an inverse element. These are the four conditions for a group. Now, if in addition the commutative property is also satisfied, then the group is called an abelian group or a commutative group. So, usually we denote a group by the underlying set and an operation star. So, if it satisfies the commutative property, if this binary operation satisfies the commutative property also, then it is called an abelian group. We also saw that there can be only one non-isomorphic group of order 3, order 2, but when you consider order 4, there are two non-isomorphic groups and they are given by these two tables. You can see these tables. For 2, the table will be like this: A, B, A, B. Then A is the identity element, so the table will be like this. For 3, the table will be like this: A, B, C, A, B, C. A is the identity element. Now, we can see that here A is its own inverse and B is its own inverse. Here A is its own inverse and B is the inverse of C and C is the inverse of B in this table. Not only that, you see that these tables are symmetric. If you look at it as a matrix, it is symmetric about the diagonal. So, they are commutative groups. If it is symmetric about the diagonal, it is a commutative group. We can very easily see that if you look at groups of order 4, there are two non-isomorphic groups. In this one, alpha is the identity element and gamma is its own inverse, beta is the inverse of delta and delta is the inverse of beta. In this table, alpha is its own inverse, it is the identity element, beta also is its own inverse, gamma also is its own inverse and delta also is its own inverse. That is why you are having alpha, alpha, alpha in the diagonal. Now, you look at the diagonal and this, you see that it is these matrices are symmetric about the diagonal, and so again these two groups are commutative groups or abelian groups. We have also seen an example of a non-commutative group by taking non-singular matrices, non-singular 2 by 2 matrices in the last class. That is an example of a non-commutative group under matrix multiplication. Now, let us see what are generators of a group. Generators and what are cyclic groups. Take a group with a set A and an operation A star. Consider a subset B of A. Let B1 be the set consisting of elements from B and elements of the form AI star AJ, where AI, AJ belong to B. Consider a subset B of A and then take the set B1, which consists of B as well as elements obtained by performing this operation on elements from B. Take B1 and perform the set B2 like this from B. Construct the set B2 from B1 and B3 from B2 and so on. B star is the union of all, or B star in the end you get B star. B star is the union of all these things. So, you consider B star and star. B star is a closed, it is a closed set, it is closed under this operation. Now, you must also consider that B should also contain the identity element, then B star star is a subgroup, it is a subgroup, and that is generated by B. You say that it is B contains the identity element of A also, A star. Then B star star is closed. So, because it is closed, you get it is a subgroup generated by B. For example, and B is called a generator. B is called a generator. Look at this example. Of rotations about a plane. The set A is taken as the set of rotations 0 degrees, 60 degrees, 120 degrees, 180 degrees, 240 degrees, 300 degrees. We have seen that under composition of rotation, which is denoted by this symbol, say, this is a group. And you can see that 60 is a generator. Generator for this, because with you combine 60 with 60 you get 120, and with that you combine 60 you get 180 and so on. So, 60 is a generator for this. Similarly, the set 120 and 180 will be a generator, a generating set. 120 alone is not a generator, because with 120, if you have 120, you can have 240 and 0. You will not be able to get 60, 180, 300. So, this is a generator for this group, and this combined set is a generating set for the group A star. Now, if you have a single element as a generator, if a single element is a generator, the group is called cyclic. The group is called a cyclic group. Now, for example, this is a cyclic group and 60 degrees is a generator for this. So, in a cyclic group, suppose I have a group A star and A is a generator, it is a cyclic group and A is a generator. Then if you take any element B belonging to A, then B will be of the form A power I. For some I, B you can express as A power I, because A squared, A cubed, everything belongs to the set A. So, if you take any element B, B will be, you can write B as A power I. Because of this property, what do you get? If you take two elements B and C belonging to A, probably B you can write as B equal to A power I and C you can write as A power J. Any element you can write in this form. So, what can you say about B star C? B star C will be A power I star A power J, that you can write as A power I plus J. And that is the same as if you take C star B, that is A power J star A power I equal to A power I plus J. From this you get B star, if you take any two elements, B star C will be equal to C star B. That is, the group is commutative. So, any cyclic group is commutative. But it is not the other way around. Any commutative group need not be cyclic. So, look at these two tables. What is alpha? Alpha is the identity element. Take beta. What is beta squared? Beta squared is gamma. What is beta cubed? Beta cubed is beta squared into beta, that is gamma into beta delta. What is beta power 4? That is beta cubed into beta. Beta cubed is delta. So, beta cubed into beta will be alpha. So, from beta you are able to get all the elements. Beta, when you just take beta, it is beta. Beta squared will be, or beta into beta will be gamma. Beta cubed will be delta. Beta power 4 will be alpha. So, beta is a generator for this group. So, this is an example of a cyclic group, and you can very easily see that it is also commutative. Look at this group. This is commutative group, it is an abelian group, but does it have a generator? Take beta, can it be a generator? Beta squared is alpha, beta cubed is alpha into beta beta, beta power 4 is again alpha and so on. So, you will be with beta you will be able to get only beta and alpha, you will not be able to get gamma and delta. So, beta cannot be a generator. Take gamma, can it be a generator? Gamma into gamma is alpha, gamma squared is alpha, gamma cubed will be alpha into gamma gamma, gamma power 4 will again will be alpha and so on. So, with gamma you will be able to generate only gamma and alpha. These, look at these elements alpha, gamma, gamma, alpha. So, with gamma you will not be able to generate beta or delta. Similarly, take delta, delta squared is alpha, delta cubed is delta, delta power 4 is alpha and so on. So, look at these 4 elements alpha, delta, delta, alpha. So, with delta you will be able to generate only delta and alpha and not beta and gamma. So, none of the 3 elements beta, gamma, delta can be a generator. So, you realize that this is not a cyclic group, but it is a commutative group. So, we see that every cyclic group is commutative, but it is not necessary that every commutative group should be cyclic. This is one result. So, next we shall see what is meant by a coset and what is Lagrange's theorem. So, let us consider what is meant by a coset. Let us consider the example of a vending machine such that 2 coins from the set nickel, dime, quarter, half dollar, dollar are to be deposited in each purchase. If you already deposited a quarter in the machine, we might want to know what are the items we can receive if the second coin to be deposited is either a dime or a quarter or a half dollar. Similarly, you look at the example of a rotation of the geometric figures in the plane. This we have considered again and again. Suppose an initial rotation is either 0 degrees or 120 degrees or 240 degrees. Afterwards, it is followed by a subsequent rotation of 60 degrees. Then what is the result? With 0 and 60 you will get 60, with 120 and 60 you will get 180, with 240 and 60 you will get 300. We want to know all the possible total angular rotations obtained like this. So, in general what we want is this, putting in a formal manner, what we want is this: let A star be an algebraic system where star is a binary operation. Let A be an element of A and H be a subset of A. The left coset of H with respect to A, which we shall denote by A star H, is a set of elements of the form A star X where X belongs to H. I shall repeat this definition. Let A star be an algebraic system where star is a binary operation, and let A be a particular element of A and H be a subset of A. Then the left coset of H with respect to A is defined in this manner. It is defined as A star H and it consists of the set of elements A star X where X belongs to H. Similarly, the right coset of H with respect to A, it is denoted as H star A, is the set of elements of the form X star A where X belongs to H. So, if you look at the examples which you consider in the case of a vending machine, first you deposited a quarter and then you want to know what is the result when you deposited a dime, quarter or a half dollar. It is in essence you are finding the left coset of the set dime, quarter, half dollar with respect to a quarter. And in the case of the rotations of the geometric plane, you have seen that first initial rotation is 0, 120 or 240 followed by a rotation 60 degrees. That is, in essence you want to determine the right coset of the set 0, 120, 240 with respect to 60 degrees. So, this is the essence of right coset and left coset which we have seen now. Immediately we get one small result. Let A star H and B star H be two cosets of H, two left cosets with respect to two elements A and B. Then either A star H and B star H are disjoint or they are identical. Now, first of all, what is H, what is A, what is B, that we have to specify. That is, you are considering a group A star and a group and a subgroup H star with respect to the same operation, and H is contained in A. Now, A and B are two elements belonging to A. Now, we are considering A star H and B star H. These two are either disjoint or they are identical. How do you go about proving this? Suppose A star H and B star H are not disjoint. Okay? They have a common element F and have a F as a common element. In this case, you show that A star H and B star H are identical. That is, A star H contains an element F, F also is in B star H. Therefore, there exists H1 and H2 in H such that F is equal to A star H1 equal to B star H2. So, you have F is equal to A star H1 and that is equal to B star H2. So, what can you say about A? A is equal to B star H2 star H1 inverse. Because of group property, you can have like this. A is this. Now, take some element in A star H. It will be of the form A star H3. Any element here will be of the form A star H3 and that will be of the form B star H2 star H1 inverse star H3. Now, you look at this, because of the associative property I can group like this. H2, H1, H3, they are all elements of H. So, this will be an element of H. So, this you can write as say B star some H4. So, if you take an element A star H3, some element X which belongs to this, you can also write X as this. So, if X belongs to A star H implies X belongs to B star H. Okay. So, look at this. For any element X in A star H, since X is equal to A star H3, for some H3 in H, we have X is equal to B star H2 star H1 inverse star H3, which is an element in B star H. Because this whole thing H2 star H1 inverse H3 is an element in H. So, that means X belongs to A star H implies X belongs to B star H. In a similar manner, you can prove that if X belongs to B star H, X belongs to A star H. The other way around, you can, the converse of this you can prove. That means these two are identical. So, we show that if they are not disjoint, they are identical. In a similar way, we can show that any element in B star H is also an element in A star H. We thus conclude that the two sets A star H and B star H are equal. In the case when they are not disjoint, they could be disjoint. So, either they are disjoint or if they are not disjoint, they will be equal, they will be identical. this gives you the result that the order of any subgroup of a finite group divides the order of the group. Now, we are considering only finite groups. Let us take the example of the rotation again. You have 0, 60, 120, 180, 240, 300. What is the order of the group? Order is the number of elements here, it is 6. Now, what are the subsets here? Subgroups 0, 120, 240 is a subgroup with the same rotation operation. Okay, this star is a subgroup. And what is the order of this? The order of this is 3. Again 0, 180 with the same operation of rotation is a subgroup. And what is the order of this? Order is 3, 2. The order is 2 here. So, you see that the order of the subgroup divides the order of the group. Here also the order of the subgroup divides the order of the group. So, as an example we have verified, and we can prove that if you have finite groups, the order of any group of a subgroup of a finite group divides the order of the group. This follows from the previous result that if you have H as a subgroup, then A star H and B star H are either disjoint or they are identical. Now, take a group A star, this is a group, take a subgroup H star. Now, let the order of this be K, then the order of this is say L. Now, you have to show that L divides K. Now, if you consider the left cosets of this with respect to each element, what can you say if you take a left coset with respect to an element, what can you say about the size of this set? This is a subset of A, of course this should be a subset of A, and what can you say about the size of this? This will be L, because you cannot have some A star H1 equal to A star H2, because in that case, because of left cancellation, H1 and H2 will become equal. So, different elements in H, when you pre-multiply by A, will give you different elements. So, the size of this coset A star H will be L. So, if you take any left coset of H, the size of that will be just L, the same as the size of the subgroup. So, and we know that from the previous result that the cosets, left cosets are either disjoint or identical. So, what H does is H partitions A, H partitions A into blocks of size L. Now, one question one may ask is every element of A taken care of? Every element of A will belong to one of these left cosets, because H contains the identity element. So, if you take any element A star E is equal to A, so every element A belonging to A will be in one of the left cosets. So, you can see that H partitions A into blocks of size L. So, suppose number of such blocks is m, then you see that m into L is equal to k, or L divides k. M is an integer because the number of blocks is an integer. So, you get the result L divides k, or the order of a subgroup divides the order of the group if they are all finite. And this example again illustrates this. This group has order 6, you have two subgroup, one is of order 3, 3 divides 6, here another subgroup of order 2, 2 divides 6. Any other example you can take and verify. If you have a group of a finite order and a subgroup again of that, then the order of the subgroup will divide the order of the group. This is known as Lagrange's theorem. So far we have seen a few results about groups. There are so many other results about groups, but our idea in this course is to give you a brief glimpse of what is meant by a group and how the concept will be useful, and also a few main important results. Next we shall see what is meant by a ring, an integral domain and a field. So far we have considered one binary operation, a set with one binary operation for semi-group, monoid and group. Now we will consider two binary operations and see what is a ring. An algebraic system A plus dot, these are binary operations, this is the underlying carrier, is called a ring if the following conditions are satisfied. A along with this binary operation is an abelian group. A along the other binary operation is a semi-group. The operation dot is distributive over the operation plus. If these three conditions are satisfied, the system is called a ring. An example of that will be, consider Zn, which is integers from and A plus B mod n addition equal to A plus B if A plus B is less than n. This is equal to A plus B minus n if A plus B is greater than or equal to n. That is mod n addition, and A dot B is the remainder when AB is divided by n. If you define these two operations, that mod n division, this is mod n division, this is mod n multiplication, and this is mod n addition. In this case, we have already seen that this is a group, and this operation is also commutative. So without loss of generality, you can see that Zn dot is an abelian group Consider Zn da. This we can see that with respect to this operation, this is closed. If you multiply 2 and then divide by n, you get another element. The remainder will always be one of the elements between 0 and n minus 1. So it is closed with respect to this multiplication, mod n multiplication. And associative property also without much difficulty you can prove. So this is a semi group. Then you can show that this operation is distributive with respect to this. This again also is a routine procedure. Without any difficulty, we can prove that this is distributive with respect to plus. So, all these three conditions are satisfied. So, this example Zn plus dot, this is a ring. This gives you an example of a ring. Now, in this case 0 is the identity for this operation in this example. In general, if you take this ring and 0 the identity for this for plus operation, additive identity, you call it as additive identity. 0 is the additive identity. Then you can see that 0 dot A is equal to 0 equal to A dot 0. How do you get this? 0 dot A is equal to 0, you can write as 0 plus 0 dot A, and because of distributivity this you can write as 0 dot A plus 0 dot A. So, 0 dot A is 0 dot A plus 0 dot A, that is 0 dot A becomes the additive identity, but you know that the additive identity is 0. So, 0 dot A is equal to 0, and similarly you can prove that this is also equal to A dot 0, right. So, the additive identity becomes the 0 element of for this operation. We can call this as multiplication, this as addition. So, the additive identity becomes a 0 for the multiplication operation. So, with this let us see what is meant by an integral domain. Again you have a set with two operations A plus dot, this is we call as addition and multiplication. It is an algebraic system with two operations, and this is called an integral domain if the following conditions are satisfied. The first condition is the same as for ring. A plus is an abelian group. Then the second condition is dot is a commutative operation. Furthermore, if C is not equal to 0 and C dot A is equal to C dot B, C is not equal to 0 and C dot A is equal to C dot B, then A is equal to B. Left cancellation you are allowing. 0 is the additive identity. The operation dot is distributive over the operation plus. That is the third condition. An example of an integral domain is a set of integers with plus and multiplication. You know that I plus is an abelian group where 0 is the additive identity, 0 is the additive identity, and if C is not 0, C multiplied by a number A and C multiplied by a number B will imply A is equal to B. This condition will be satisfied, and multiplication is distributive with respect to addition, and so all the three conditions are satisfied. So, this is an example of an integral domain. Next we shall see the definition of a field. What is a field? Again we have two operations, addition and multiplication. let A plus dot be an algebraic system with two binary operations. This is called a field. If A plus is an abelian group and 0 is the additive identity, then A minus 0 dot is an abelian group. The operation dot is distributive over the operation plus. If these three conditions are satisfied, it is called a field. Consider a set of real numbers, the plus operation and the dot, that is addition and multiplication. R is a set of real numbers. R set of is the set of real numbers. Then you see that R plus is an abelian group, that condition is satisfied. What is the additive identity? 0 is the additive identity, and R minus 0 dot, this will be a group where 1 is the multiplicative identity. Here 0 is the identity, here 1 is the identity, and the inverse of x inverse will be minus x here. Here x inverse will be 1 by x. So, inverse exists. So, this is again an abelian group. Both addition and multiplication are commutative operations. So, this is an abelian group, this is an abelian group, and you know that multiplication is distributive with respect to addition. So, the third condition is also satisfied. So, this is an example of a field. And similarly, you can see that if you take the set of complex numbers, the plus operation and the multiplication of operation, this is also a field. And if you take the set of rational numbers, which usually you denote by Q, plus dot is a field. Q is a set of rational numbers. Now, look at this. Is this a group? Set of integers plus dot. Is this a field? This is not a field because the first condition I plus is a group is okay, but I minus 0 dot is not a group, because if you take some element 3, what will be the inverse of 3? You have to define it as 1 by 3, because 1 is the multiplicative identity, but that is not an integer. So, here the existence of inverse we cannot prove. So, this is not a group. So, because of that, this is not a field, this is not, it is an integral domain, but not a field. Similarly, if you consider Zn plus dot, then this is a field. You can check this. This is a field if and only if n is a prime. If n is a prime, certain properties will be violated and you will not be able to get a field. So, this is a field if and only if n is a prime. So, we have seen the definition of ring, integral, domain and field and some examples. Next, we shall consider a few problems. Look at this problem. Let n be the set of all natural numbers. For each of the following, determine whether star is an associative operation. Take A star B is defined as maximum of A and B. We can very easily see that this is an associative operation, because A star B star C, we take, this will be maximum of A comma maximum of B comma C. In essence, you will be really finding the maximum of A comma B comma C. Similarly, this will be equal to A star B star C. Again this you will be finding the maximum of these 3 elements. So, this is an associative operation. Take the fourth one. A star B is defined as A plus 2B. So, what is A star B star C? That will be A star B plus 2C, and that will be equal to A plus 2 times B plus 2C, that will be A plus 2B plus 4C. What can you say about A star B star C? And that is A plus 2B star C equal to A plus 2B plus 2C. We can see that this is different from this. So, in this case star is not associative. We can try the other 2 portions. Let us consider one more example. Let A star be an algebraic system such that for all A, B, C, D in A star A is equal to A and A star B star C star D is equal to A star C star B star D. Show that A star B star C is equal to A star B star A star C. Let us take the right hand side of the result we want to prove. The right hand side is A star B star A star C. Now, use this rule. This rule is A star B star C star D is equal to A star C into B star D. We use this rule, you will get this is equal to A star A star B star C. But we are also given that A star A is A. So, make use of that, then you will get A, this is replaced by A star B star C, which is the left hand side. So, we have proved the result. Let us consider some more examples. Let A star be a semigroup. Furthermore, for every A and B in A, if A is not equal to B, then A star B is not equal to B star A. Or if A star B is equal to B star A, that will imply A is equal to B. Okay. So, this is a semigroup. For semigroup, closure and associative property hold, and the condition given here is A not equal to B means A star B not equal to B star A. The other way around, you can say that if A star B equal to B star A, then A is equal to B. This is the contrapositive. So, 3 results you have been asked to prove. Show that for every A in A star A is equal to A. So, A star A is equal to B, say. Then what can you say about B star A? B star A is A star A star A, and because of associativity you can write it as A star A, that is equal to A star B. So, you have B star A equal to A star B, which implies B is equal to A, that is A star A is equal to A. In a similar manner, we can prove 2 and 3 also, second part and the third part. What is the second part? Show that for every AB in A, B star B star A is equal to A. Look at A star B star A. Suppose this is A, then C is A. Then C star A is A star B star A star A. But A star, because of associativity, you can write like this. A star A is A by the first part. So, this will be A star B star A. What can you say about A star C? A star C is A star B star A, and because of associativity you can group like this. By the first part, A star A is A. So, A star B star A. These two are equal. So, you get C star A is equal to A star C, which implies C equal to A. That is A star B star A star B star A equal to A. This is the second portion. Let us look at the third portion. Show that for every ABC in A star B star C is equal to A star C. Let A star B star C equal to say some D, and A star C is some F, say. Then D star F is equal to A star B star C star A star C. Because of associativity, we need not put parenthesis, but you know that C star A star C by the previous part, second part, this will be equal to C. Now, what can you say about F star D? That will be A star C star A star B star C. This like this, and because of associativity you can remove the parenthesis and write like this. Now, if you take this alone, it is A star C star A. So, by the previous second result, this will be A, this portion will be A. So, you get A star B star C. So, you find that these two are equal, that is D star F equal to F star D, which implies D is equal to F. This implies D is equal to F, that is A star B star C is equal to A star C. So, we have proved the third part also. There are some more examples which you can try as exercise. One is, let A B, there are only two elements in the set and star is a binary operation, and we have also A star A is equal to B. You are asked to show A star B is equal to B star A, and you are also asked to show B star B is equal to B. This is again a very simple example which will immediately follow by the associative property of the semigroup. Now, this A star A is a semigroup. Show that if A is a finite set, there exists A in A such that A star A is equal to A. This is not as simple as this, it is slightly more involved, because all the powers of an element, if you take that, belongs to the semigroup because of the closure property, and you are also given that it is a finite set. That has to be taken into account. So, in this lecture we have seen Lagrange's theorem and a few more properties of groups and how to tackle some problems about groups. So, this covers the topic algebra and varieties of algebra.